Welcome to Chapter 4 of the Autonomous Driving series. In this chapter, we explore the critical infrastructure behind self-driving vehicles, simulation platforms for safe testing, mapping technologies for navigation, and the regulatory frameworks governing deployment. These three pillars determine how quickly autonomous vehicles can move from the lab to public roads. By the end, you'll understand why companies invest billions in virtual testing and why regulations vary so dramatically across regions. CARLA is the most widely used open-source autonomous driving simulator. Built on the Unreal Engine, it ships with a set of pre-built urban maps and a large library of vehicle models for realistic multi-agent simulation. What makes CARLA powerful is its multi-sensor simulation. You can attach cameras, LiDAR, radar, GPS, and EMU sensors to any vehicle and collect pixel-perfect ground truth data. The Python and C++ APIs let researchers script complex traffic scenarios, inject weather changes, and spawn pedestrians. Research teams worldwide use CARLA because it generates thousands of hours of labeled training data without putting anyone at risk. NVIDIA Drive Sim takes simulation to enterprise scale using the Omniverse platform. Unlike game engine simulators, Drive Sim provides physically accurate sensor models. Its ray-traced LiDAR returns match real sensor hardware, camera models include lens distortion and motion blur, and radar simulation accounts for material reflectivity. The platform is cloud scalable, meaning you can run thousands of simulation instances in parallel to test edge cases. A key feature is hardware-in-the-loop testing, where the actual driving computer receives simulated sensor data in real time. Companies also build digital twins of real cities, replicating exact road geometries and traffic patterns to validate their systems against specific deployment locations. High-definition maps provide centimeter-level precision, far beyond what consumer GPS offers. An HD map consists of multiple layers. The base layer contains satellite imagery, the geometric layer defines exact lane boundaries and road edges, the semantic layer encodes traffic rules like speed limits and signal phases, and the dynamic layer adds real-time information like construction zones. This rich data allows autonomous vehicles to know exactly where they are and what rules apply before their sensors even detect the surroundings. However, HD maps are expensive to create. Surveying and maintaining a single kilometer of road costs thousands to tens of thousands of dollars, and any road change requires updates. This cost and maintenance burden has driven the industry to explore alternatives. The autonomous driving industry is undergoing a fundamental shift away from HD maps. Tesla led this movement by eliminating HD maps entirely, relying purely on real-time camera perception to understand road geometry and traffic rules. XPeng followed with lightweight maps that store only basic road topology. Huawei's ADS system uses a general obstacle detection network to perceive the environment without pre-built maps, and Li Auto deployed its navigation assist feature without HD map dependency. The motivation is clear: HD maps don't scale. You cannot map every road in every country and keep it current. The hybrid approach offers a middle ground, using pre-built course maps for general routing while relying on real-time perception for precise navigation. This shift has profound implications for how quickly autonomous driving can expand geographically. Japan and the United States represent two contrasting regulatory approaches. Japan legalized Level 4 autonomous driving in April 2023, making it one of the first countries with a comprehensive L4 framework. The Japanese government has pushed for social implementation across many regions, particularly for last-mile transportation in aging rural communities. The United States takes a state-by-state approach, and a large majority of states have passed some form of autonomous driving legislation. California, Arizona, and Texas are among the most permissive, allowing driverless testing and deployment. However, there is no federal Level 4 framework. NHTSA provides federal guidelines, but each state sets its own rules, creating a patchwork that companies must navigate individually. The European Union operates through UN regulations, with UN R157 establishing the Automated Lane Keeping System, standard for Level 3 highway driving. It was first adopted with a low-speed ceiling for traffic jam use and has since been amended to permit substantially higher motorway speeds. Germany became the first country to enact a comprehensive Level 4 legal framework, setting the global benchmark. France mandates black box data recorders in autonomous vehicles, ensuring accident accountability. China has taken an aggressive pilot approach, designating a large number of cities for autonomous driving testing. A selected group of companies has been approved for Level 3 testing, with Beijing, Shanghai, and Shenzhen leading deployment. China's approach combines top-down government direction with rapid iteration in designated zones, allowing the technology to develop quickly within controlled boundaries. Autonomous vehicles must comply with a hierarchy of safety standards. At the foundation is ISO 26262, the functional safety standard that defines automotive safety integrity levels from A to D, with D being the most stringent. Steering and braking systems require ASILD certification. Above that, ISO 21448, known as SOTIF or Safety of the Intended Functionality, addresses a different problem. What happens when the system works as designed, but encounters scenarios it wasn't designed for, like unusual lighting conditions or unexpected objects? ISO SAE 21434 covers cybersecurity engineering, ensuring that over-the-air updates and connected vehicle systems cannot be compromised. Together, these standards form a comprehensive safety framework that covers hardware failures, edge cases, and cyber threats. Responsibility-sensitive safety, or RSS, is Mobileye's approach to mathematically defining safe driving behavior. Unlike statistical safety claims based on miles driven, RSS defines a formal safety envelope. Given stated assumptions about how other road users behave, it can be proven that the vehicle will not be the cause of a collision. The model defines safe distances for every driving situation. Longitudinal following distance accounts for reaction time and braking capability, while lateral distance ensures safe lane changes. RSS establishes 5 core rules covering safe following distances: right-of-way respect, caution in limited visibility, crash avoidance responsibility, and proper response to dangerous situations. The key formula calculates minimum safe distance based on current speed, reaction time, and maximum braking capability of both vehicles. This mathematical approach means safety can be verified before deployment rather than validated through billions of test miles. Let's review the key takeaways from Chapter 4. Simulation platforms like CARLA and NVIDIA drive sim-enabled testing at massive scale without real-world risk, using physically accurate sensor models and digital twins. Physically accurate sensor models and hardware-in-the-loop testing let teams validate the real driving computer against simulated inputs. The industry is shifting from expensive HD maps toward mapless approaches that scale globally. On the regulatory front, Japan leads with its Level 4 legal framework, while other regions are developing their own approaches at varying speeds. Safety standards from ISO 26262 to SOTIF to RSS define formal requirements that autonomous systems must meet. In Chapter 5, we'll explore the market landscape, key players, business models, and the future outlook for autonomous driving technology. See you in the next chapter.